Hello everyone, in the previous lecture we have discussed about the CSTR. Now in this lecture we will discuss about the PFR reactor. The PFR reactor, the plug flow reactor. Now what will be the plug flow reactor? It is the reactor like simple 5 in which the reactant A enter into it and the product B is produced. The reactant A here is converted. It is a plug flow reactor. It is like a 5. This is a plug flow reactor. Now, as we have already discussed, the CSTR is usually used for the liquid phase reaction, for the liquid reactions, liquid phase reaction. The PFR is used, usually it is used for the gaseous reaction, used for the gas phase reaction. Now what will be the mole balance for the PFR? Now generally, as we know that input minus output plus generation is equal to accumulation. Now in the case of PFR, suppose this is our PFR. In the case of PFR, suppose this is Fa, flow rate of A. This is flow rate of A at the outlet. This is at the inlet. It is in the inlet. Now for mole balance we consider a small volume in the PFR. Suppose this is the small volume. This is the small volume. It is like a 5. It is a circular. It is like this type of volume. This type of volume, the whole volume. It is like this. Consider this volume. We consider this is the zoom of this volume. If we zoom it, we will get this type of volume. The flow rate of A here is Fa at volume V. Now this is the flow rate of A at some V plus delta V. Here this is the volume V and here is volume plus delta V. This is the small volume. It is so small that the rate of reaction here is constant. Rate is very small, as we have assumed in the CSTR. It is so small volume that the rate of reaction here is constant. It is considered to be constant, and it is our assumption. So if A at the volume V and here if A at the volume V plus delta V. Fa at volume V plus delta V. Now from our general mole balance equation, this is the general chemical reaction engineering equation. So in case of component A, for the case of the small volume, which we have already considered, this is Fa V plus delta V. This is flow rate of A at volume V. This is the small volume. The rate here is constant in this volume. So Fa at volume minus Fa at volume V plus delta V, and here the generation term is Ra delta V over the volume, and at steady state the plug flow reactor or the PFR is actually operated at steady state, so the accumulation term is 0. Now if we say after simplification, we get FA V minus FA V plus delta V RA dV is equal to 0. Now this RA is constant, so it come out from the integral sign, and this dV is the small change in volume. This was the small change in the volume. This was the delta V. Now the FA minus FA volume plus delta V plus RA into delta V is equal to 0. Now we can rearrange this equation. RA delta V is equal to FA V plus delta V minus FA V. Now divide this equation by divide this side by delta V, both side by delta V. It will be RA is equal to FA flow rate at V plus delta V minus flow rate of A at V divided by volume. Now let the volume tend to 0. At very small volume, this relation will become dFA divided by dV, which is a differential form, and which is nothing but rate of A in the small volume. So this is the differential form of the differential form for the plug flow reactor. Now in plug flow reactor we have some assumption that one assumption was RA was constant. The other assumption was it work for turbulent flow. The flow here was turbulent flow. The velocity profile was quite flat. It was quite flat velocity profile. There was no radial change in the velocity. There was no velocity boundary layer. Like in fluid mechanics, we know that the velocity parabolic velocity profile is formed in the case of laminar flow, as we have already discussed in fluid mechanics. So in here we have taken the assumption that the flow is turbulent and the velocity profile is flat, and there is, suppose this is the R direction and this is the velocity. So the velocity changes in the R direction in the case of laminar flow. Like as the R increases, the velocity decreases and tend to 0, and at this place the velocity of fluid is 0. It is equal to the velocity of the pipe, which is constant and 0, which is known as no slip condition. So here we, for simplicity, we take the assumption that the flow is turbulent. Now we have obtained the differential form dFA by dV is equal to RA. For any reactant dFA, for any reactant dFI, for any reactant I dFI divided by dV is equal to RI. Now in the plug flow reactor, in the axial direction, which is the volume or length of the reactor, as the length or the volume of reactor increases, the conversion or the concentration of A decreases and the concentration of B increases in the case of plug flow reactor. Now this was all about the plug flow reactor. Now for the integral, now what will be the integral form of the equation For Follicle reactor, dFA dV is equal to RA. This was the differential form for the Follicle reactor. Now we can also write it in the integral form, like dFA by RA is equal to dV. Now this is the differential form. Now we can integrate this relation, like at volume V is equal to 0. The flow rate of A was FA naught. FA was FA naught. Now at volume V is equal to V, the flow rate of A was FA. So this is the integral form of Follicle reactor. Like we have made some assumption that suppose volume here is 0, flow rate here is FA naught, and the volume here is V, and the flow rate here is FA. So this is the integral form of the Follicle reactor. Thanks.